Good morning, everybody. Today, there isn't actually a Code Forces round, but there's this unofficial Code Forces round called Noobs Round 2. It's a Division 4 round by Rudo25. Here you go. So there's the round title. At the moment, there is about an hour left, and I thought I would go over the solutions to all the problems. I helped prepare the round a little bit. I published it in the gym, so you'll see it's by me. But the problems were written by Rudo25. And interestingly, one of the coordinators for this round was Madigan. So that's kind of a fun fact. He's a good friend of mine, and yeah, I've talked to him quite a bit. Maybe you'll see him on the channel sometime. We'll see. Anyway, okay, so let's jump into the problems, and we can talk about them. For this first problem, directional move, you've got a binary string that is of length n, and consists of only zeros and ones. So if it's a 0, it means you should turn left. If it's a 1, you should turn right. The question is, what direction will you be facing if you follow all of the commands? So in this case, you would turn right, and left. So you'd be facing the same direction you started, assuming that you start facing east. Yeah, initially you're facing east. So that's the problem. How do you do it? Looks something like this. You've got multi-test cases, and in this case, it was single test case when I tested it, but yeah, oh well. For each of the moves, in this case, what I do here is this is a kind of convoluted way of increasing my position by 1 if it's a 1, or decreasing it by 1 if it's a 0. So 2 times this will be either 0 or 2. If you subtract 1, that's either +1 or -1. And at the end, I take my position mod 4. So the 4 directions are north, east, south, and west. And then I take the position character of that. So this is one way of solving it. There are other ways. You could just do an if statement here if you wanted to be a little bit more clean. So you could do it if it's equal to 1, add 1, otherwise subtract 1, or I forget the exact order. But yeah, that's the idea. At the end, you print out the answer. So that's one way to solve problem A. Hopefully that made some sense. Let's talk about problem B, make it all odd. In this problem you have an array of n integers. You want to make all of the integers odd, and what you can do is pick 2 integers and replace the first one with the sum of the first 2. So maybe let's look at an example. In the first case you have you've got 4 integers, 1, 4, 3, and 2, and you can make them odd by picking 2 integers, replacing maybe the 4 with a 1. So in that case, you replace the 4 with a 1, or you replace the 4 with 4 plus 1, which is 5, and then maybe you could replace the 2 with 5 plus 2, which is 7. So in total, that takes 2 moves, so we print 2. It's also possible that, or it also might be the case that it's impossible to solve some particular problem. In the last case, that's what happens. If you keep adding any of the numbers, it's always going to be, all of them will still be even. So there's no way to get around that. There's no way to make any of them odd, actually. So obviously you can't make all of them odd. Okay, so what's the general approach to this problem? Well, if you add an odd number to any other number, it'll change whether that other number is odd or even. An even number won't change whether the other number is odd or even, and since our goal is to make everything odd, we're only going to add odd numbers to other things. So if the array has no odd numbers, like in the last case, then it's impossible. If it has any odd numbers, then each move, what we'll do is pick one of the odd numbers and add it to an even number. That will remove one of the even numbers and make it odd, and we can keep doing that till we run out of even numbers. So either the answer is it's impossible, or the answer is the number of even numbers. Here's my code for that, which does exactly what I said. So we have some array of size n. We read in the array of size n. I'm going to count how many numbers are odd and how many are even. So if this number mod 2 is 0, that means it's even, otherwise it's odd. And then finally, at the end, if the odd count is 0, if there are no odd numbers, then it's impossible, so I print -1. Otherwise, I print how many even numbers there are. That's the entire problem. Okay, hopefully that made sense. Let's move on to problem C, which is team. So in this problem, you're given the programming skills of n different students as some array. You want to make a bunch of teams for the programming contest, and a team is the sum of the skills for each student, and a team is also just like a pair of students or just one student by himself. The sum of each skill level of each team's skill levels must be at least k. So you want to maximize the number of teams you can make, and each student can be part of at most one team, and he might not be part of any team. So as some example, let's say you're given 5 numbers, which are these 5. These are the 5 skill levels, and you need each student or each sum to be at least 8. You can make one team by himself, that is just the 9 by himself. You can have one team that's the 2 4s, and a third team that's this 3 and the 5. So that follows all the constraints. Each team has at most 2 people, each team sums to more than 8, and no person's used more than once. What's the idea for solving this problem? Okay, so solution time. What we can do is say any person who is bigger than the highest, or bigger than k, they'll be their own team. It's not helpful to pair them up with anyone else because that other person, like, they're just not even needed. So we'll just have that person be their own team, and we're fine there. Then for someone who's below whatever this max constraint is, we want to pair them up with the biggest person, or with the smallest person who's big enough. And that's the idea. There are a bunch of different ways of doing that. One way is you can use a tree set, which is what I did here, a tree map. In C++, you could use a multi-set. That'd probably be a little bit easier. Another way is you could do a 2-pointer sweep. If you sort the array, that would work as well. So for this tree map, I have a tree map. This first okay, well, I guess first what I do is I have this integer n and also my target value. Now I read in the array, and this tree map maps for each number, how many times does it appear. So then for each index in the array, or for each element in the array, I increment how many times that number appears. So if it's already in the map, then I'll get however many times it previously appeared. If it's not in the map, I just get 0. I add 1 to that number, and I put that back in the map for the same thing. Now this count is the number of pairs I have, and then at the end, I'm going to make as many pairs as I can, and then finally print it. So to make a pair, at first I get the smallest number in the map. So the smallest number that I haven't used, the worst person, least talented person, I guess. I get them. If there's only one of them, then I need to remove this key. Otherwise, I just decrease how many of them there are. Okay. So now, if this person is already good enough to be on his own team, then I make him his own team, I add one more team, and then I keep going. Otherwise, the amount of help this person needs is the target minus first. So I get the next person with at least that much skill, at least that skill level. That's this. If that person doesn't exist, that means this person doesn't have any possible partners, so we'll get rid of them. Otherwise, we'll match them up with the least talented partner that they need. That's what this does here. So we get them. If it's not null, then I decrease it by 1 in the same way that I did up here. So I decrease it by 1 here, and then I increase my count. And that is problem C. Hopefully that made some sense. Okay. Let's look at problem D, or problem D. Yep, XOR game. So this was actually one of my favorite problems. I thought it was very interesting. And I'll talk about the solution here. I guess I'll walk through a couple examples to help you understand how I got there as well. So in this case, you've got 2 players, Alice and Bob. Alice chooses 2 integers A and B. Then Bob will pick 2 integers C and D. The score of Alice will be A XOR B, and the score of Bob will be C XOR D. So Alice will already pick her 2 integers, and basically pick her score as well. Now Bob, you have to pick C and D, so that you get a strictly better score than Alice. But also, C can't be bigger than A, and D can't be bigger than B. Okay, so you know A and B. You want to see if Bob can win by picking C and D. Let's look at an example with whiteboard. What is this? Almost okay. So let's say maybe in the first case they both picked 2. So they pick 1, 0, or both the numbers are 2 and 1, 0. You have to pick two numbers both less than these. So one thing you might pick is instead of this, you could pick 0, 1. Then instead of this, you could pick 1, 0. So this first number is greater than or equal to the one you pick. This number is greater than or equal to this. The XOR of these things is going to be 0. The XOR of these is equal to 3. So your 3 is better. Now here's the observation, which is XOR can do a few things. An XOR can add a bit, can subtract a bit, or if the thing is 0 here, it's going to leave the bit the same. So you can't ever like turn a 0 to a 1 if that's the only thing that you change. And that would change you from leaving a bit the same to adding 1 to it. The only other improvement you can make is if there's some 1 in this answer, for instance this 1 here, you could make it from a 1 to a 0 if that 1 is unhelpful, if that 1 subtracts a bit from the top number. In this case, that's exactly what this 1 is doing. If we didn't XOR it, we would have 1, 0, but since we do XOR it, this 1 removes this bit. It turns the bit off. So if we didn't turn the bit off, we would have a bigger answer, a bigger XOR at the end, which is a bigger score. That's our target. So what we can do is we can turn this bit off. So we can change it from 1, 0 to 0, 0. I think that's the idea. And interestingly, I think is there weak data on this problem? Ooh, I might have a bug. This is fun. Well, yeah, look at this. This is kind of cool. Unless I'm just being silly here. Okay, so what is the answer to 1, 1? The answer is yes, but it should be no. So interestingly, this has somewhat weak data. Yeah, okay. Well, that's fine. Or it did originally, at least. Maybe not now. Maybe more data was added, hopefully. Okay, so if you could pick 0, that's the right solution. You can't pick 0, though, so you have to, I guess, watch out. And, yeah, let's talk about that. So, in the event both of the numbers are 1, then the answer is going to be no. So if A equals 1 and B equals 1, then sys out no. And return. Okay. Otherwise, if the XOR is non-zero, you can decrease whichever one is bigger. You can decrease one of the bits in whichever one is bigger. After that, then you should be set. So I think this is the only break case where my code is actually wrong, interestingly. So yeah, that's fun. That's fun. Okay. Anyway, yeah, let's look at why that's the case. So if you've got some numbers, maybe you've got like 0, 1, 1, 0, 1, 0, and 0, 1, 0, 0, 1. In these numbers, they share this bit, which means what we can do in order to get a better score is get 0, 1, 0, 1, 0. We can leave this number the same. This number we can make 0, 0, and now instantly we'll have this bit on. So everything after us will have a better score for. So now we can make these whatever we want. We can just leave them the same. How about that? 0, 0, 1. Now if this number is a 0, we'll make it a 1. And we might lose a point for that, but we're gaining, in this case, 2 to the 4 points. 2 to the 3 points. So we're gaining 8 points. We might lose 1 point. That's fine. Not a big deal. Okay, yeah, so that's the idea. I guess special case when they're both 1s. Hopefully that was additive data, and you should be good. Otherwise, the answer, or the solution is check whether they share any bits, which you can do with bitwise and. All right, little hiccup. Anyway, we should be fine there. Problem E, password. So you're given some string, and in this case, you want to replace all of the hyphens with either digits 1 through 9. The question is, how many ways are there to do that under mod? So in this first example, there are 4 options. You can have a 1 and then a bunch of 2s. You can have 2 1s and then 3 2s. You can have 3 1s and then 2 2s, or you can have 4 1s and 1 2. 4 different ways of doing that. There are a bunch of other samples here which are very similar. So there might be different ways to do this problem. You might be able to do some n choose k stuff if you want. I think the easier way, since there are only 9 digits and n is only 10 to the 5th, is to do an n times k dp, or n times alphabet size dp. So you can do a dp where your state is what the smallest number you can place is, and also which index you're at. And this equals the number of ways to do that. Your transition is you try placing like all of the numbers. From smallest all the way up to 9. You also have to watch out for the case in which this position isn't a hyphen. So if it's some number, then you have to place that number. If it's a hyphen, then you can place all of those numbers. If there's ever a decrease, so if the smallest number you can place is bigger than the number you have to place here, then the answer is 0, because we've done some illegal thing in the prefix, which means there are 0 ways to finish it. Okay, here's what that code looks like. So I have my DP. This is the last number I placed. This is my index. And initially, the DP is all -1s. The answer is, well, you're going to start with the last number you placed is a 0. You're at, or sorry. Oh, I guess this order is different. But you're at index 0. The last number you placed was a 1. So you can imagine putting a 1 in front of the answer. It wouldn't change anything, because the smallest number you can place is 1 anyway. Yeah, so what does this DP look like? If you're at the end of the line, funny, anyway, then the answer is 1. If you just have this filled out in your DP array, then the answer is whatever it was last time. So this prevents our runtime from being exponential, keeps it very fast, because we set this at the end. So for any pair of inputs, we memoize, so we only do it once for that pair of inputs. Otherwise, we brute force what we're going to place. It's some integer from 1 to 9. If it's less than the last value, then we can't actually place it here, because that's not allowed, because it's got to be strictly increasing. Otherwise, if it's a hyphen, and the other thing, okay, so if the position in the string is something that isn't a hyphen, so it's not a blank character, and it's also not what we're about to place here, then we can't place this, because we're forced to make some string. It's got to match in the positions they give us. In this case, it doesn't match, so we're in trouble. It doesn't work. Otherwise, we try placing it and then add that to the number of ways to finish. Okay, very good. That's problem E. The last problem is problem F. So this is kind of a classic problem, but we'll see. I thought it was very interesting, quite a good problem. You've got K dollars, and you want to buy some items from a shop. Got n elements arranged in a row, and for each item, the rate of the item, I guess the cost of the item, is AI. So there's this weird rule, which is if you buy some continuous subsequence, you only have to pay, here you go, you only have to pay one or once for each item of the same rate. So let's look at some example. In this example, you have $5. You want to buy as many items as possible, but you only have to pay once for each item of the same cost. So if you buy this range here, you'll have to pay once for a 3 and once for a 2, which will be a total of $5, but you'll buy all 5 items. So that's the idea. So the question is, how many items can you buy with this special rule if this is how much money you have? Okay, so the idea for this problem is we can do this thing called a 2-pointer sweep. So we'll have one pointer, which will be the left end of the range we're considering, and another pointer for the right end of the range. We'll consider moving our left pointer over from the beginning of the array all the way to the end of the array. As we do that, our right pointer will also be moving over to the end of the array. So we'll try and sweep both of them across, and we'll be able to calculate, okay, if we add this number, how will that affect our cost? If we already have one copy of that number in our range, it won't increase our cost at all. But if we don't have a copy of that number, adding this new number will increase our cost by that amount. We also have to consider when we move our left pointer over, will moving our left pointer over decrease the cost at all, or will it not? So let's say when we move the left pointer over, there's some number here that we used to have in our range, but now we won't. If there's another copy of that number in the range, then the cost doesn't decrease when we move the left pointer over. But if this is the only copy of the number in the range, then we have to pay for it now, but when we move that left pointer over, we won't have to pay for it. So it'll decrease the cost by the value of that number. Hopefully that made sense. I'll walk through the code. Maybe that'll make a bit more sense if you didn't understand that first part. Yeah, okay. Anyway, I thought it was a little bit harder. I guess maybe this was like a Div2C or something level problem. I thought it was good. It was interesting. And I didn't have time to do it originally, so that's why I did kind of poorly in the test. But anyway, so yeah, here's the idea. So I've got these arrays. Each of these store what is the next thing with this value, what's the index of the next thing with this value, and what is the index of the previous thing with this value. So that's the idea, yeah. Or I guess what's the previous thing with the same value as what's at this index? And same thing here. Last seen index is what's the last time I saw something with this index, and I do 2 sweeps here. So this is to set up the previous thing, this is to set up the next thing. Okay, so then I do my 2-pointer sweep. So L is my left pointer and R is my right pointer. And I go from both of them being 0 to L being the end of the array. So in this case, what this is saying is if my right pointer is like to the left of my left pointer, that means they were like even and I moved my left pointer over. So now I want to reset it by putting them both at the same position. So this resets it. It also sets the sum to 0. It's like, okay, my left pointer's here, my right pointer, which is exclusive, is one before it. So now we're ready to go. Yeah, I misexplained it actually. It's not if they were at the same position. It's if my range was empty. So left pointer here, right pointer would be one before it. Then I would continue going. But anyway, I guess that's not too important. Then, yeah, so here's the actual loop for the right pointer. This whole thing is a loop for the left pointer. So at the end, I increment the left pointer, and I might add to the sum if I need to. So here is to increment the right pointer. I have 2 methods to do this, which I think maybe make it easier to think about, which are I keep expanding as long as the sum of what these things is less than or equal to the money. So as long as I can afford it. If I ever expand and it's too expensive, this case means it's too expensive, then I undo that expansion. And then I break out of this while loop. If it's not too expensive, then I consider this as a possible answer. So I consider this is something that I might have. And that's the idea for the problem. So I guess I can go through one example real quick on how this might work. And then we should be good to go. So let's do this example here. We have 1, 3, 2, 2, 2, 3, 1, 3. Let's do that in Paint. 1, 3, 2, 2, 2, 3, 1, 3. Did I get that right? Amazing memory. Hoorah. Okay. So here's the idea. Initially, we'll have our left pointer here, and our right pointer will be here. We have $5 total, and on the first step, we'll consider moving our right pointer here. So we can, which means after this step, our range will look like this. Now we'll consider expanding again, and we can do that. So our range will look like this. Now we'll consider expanding again. Initially, we'll do that, and then our cost after we expand. Initially, it was $4, right? So before it was 4. Now we added a 2, so now the cost is 6. But 6 is bigger than 5, so we've just done something illegal, so we'll decrease the size of our range by 1 here. So now we'll set our cost back to 4. Okay, so we just broke out of that loop. Now we want to increase the left pointer. So we'll do that. We'll increase the left pointer here. But also, we see there isn't a 1 in this range, which means since we just decreased this 1, we got rid of this 1, we get to decrease our cost by this 1 because we no longer have to pay for it because it's not included anymore. So we can do that here. All right, now this is our left pointer, and we're going to continue increasing our right pointer for as long as possible. So the first step, we want to add this 2. We do that. Oh, our cost, I forgot to subtract 1 from the cost. The cost is now 3. So we include this 2. That will increase our cost by 2 since there isn't a 2 in this range. So now our cost is 5. In the next step, we want to include this 2, so we do. We see that the previous 2 was in this range, which means we don't have to pay for this additional 2, so the cost stays at 5, but we increase our range by 1. And that means that this is some possible answer, so our answer might be 3. We continue increasing the right pointer. So again, there's another 2 in this range, so we don't have to pay for it, and then there's another 3 in this range, so we don't have to pay for it. Finally, we would increase to this 1. We would see, okay, that would increase our cost to 6, which is too much. So we would undo that, and now this is the optimal thing we would get. We would continue increasing our left pointer, but we'd never find an answer better than this 5. Then we print 5 at the end. All right, awesome. That's the solution to F. There's one unanswered question. I guess we can go answer that right now. How about that? You guys can see what it's like to answer a question. Can you spend less than K? Yes, you can. Let me triple check, but I believe that is the case. Oh, yeah, okay, I guess that should have been explained better. Yeah, we should have said at most K, so that might be distribution of all. Yeah, so the way I'm doing it, yeah, so okay, that's valid. So let's say yes, and then I guess we will distribution all. Or maybe we don't need to. Yeah, I guess I won't. That's fine. Hopefully that's intuitive. If anyone else asks, then we'll distribution all. But yeah. All right. Well, thank you guys for watching. I hope you enjoyed the contest. If you didn't do it, it might be a fun thing to try because I thought it was a very good contest. Very interesting problems, and they're also very easy. So I guess if you're helping teach someone how to program, these are some good problems to practice with. If you're new to competitive programming, if you want someone to, I don't know, to like get their feet wet, this is a good thing to try. Because they're interesting problems, they're fun. Yeah, and that's all. Thanks for watching. Hope you have a great day, and hopefully this was helpful. Goodbye.